Good morning. I'm showing 9 o'clock a.m., so we're going to go ahead and get started. My name is Mike DeLacluse, President of Lesman Instrument Company. I'd like to thank you all for taking time out of your busy schedules to join us for Basics of Magnetic Level Measurement. Today's webinar is going to be presented by WIKA's Jim Linahan. Jim's going to teach you the basics and even get into a little deeper. He will be covering some key topics such as how they work, the best place for them to be used, some configuration options, and some sample applications. Jim is currently the Business Development Manager for WIKA Magnetic Level Indicator products. He has 25 years of experience dealing with these products with companies such as Siemens, Meltronics, Magnetrol, ABB, K-Tech. Because of the large number of attendees, we will be muting the phone lines. If you have a question, there is a question chat tool built into GoToWebinar. Please enter your question and we'll make sure we get it answered. With that, I'm going to turn it over to Jim.
All right, thank you very much, Mike, and good morning to everybody. I'm real excited to be here. It's an honor to be able to talk about magnetic level indicators, and with that, we'll get started right away. Magnetic level indicators are a product that's been around probably since, well, the way we've discovered it is there's a company called Phoenix in Germany that we purchased after we purchased KSR Kubler, and we found that this company Phoenix had been around for about 100 years, and they had been making valves and tubular glass gauges and other things. But we found that they had a patent for a magnet system that could be enclosed in a float that would cause a reaction to flags outside of a chamber. And whether or not this is the first patent for this product or whether it is the inventor of this product, we don't know, but it was in 1959, and it very well could be the first product. As I mentioned, WIKA bought the KSR Kubler company that had been manufacturing magnetic level indicators since the 70s, and then as time went on, they became more and more popular. I think in the last 20 years they've become a standard instrument for visual indication for many applications in many different industries. But we put together the knowledge from both these companies and put together our product and so on. But what I want to focus on today is how they work, what they do, and as Mike said, maybe talk about some of the ways that they're installed and so on. So with that, we'll get right after it. The main reason for this product is well, it's the biggest application, I should say, is for replacement for glass gauges. Now, reflex and transparent level gauges have their place, and they are an instrument that, once again, have been around for 100 years or so, work very well, and they're needed. It's an absolute must to have a visual indication of where a liquid level is to double check versus what the transmitter output is providing and so on. But over the years it's been discovered that, you know, these things can be a maintenance item. They do get dirty, they do fog up, the gaskets fatigue, the glass fatigues, there's valves that need to be checked, and so on. And it is I'd say a moderate to high maintenance item for many plants, although it's just a necessity. So along came the idea of a magnetic level indicator as a replacement for this type of an instrument. So how does it work? And this is just kind of a very brief description of how it works, but basically what we do is we manufacture a chamber, a basic pipe chamber, and we connect it to the tank of a liquid to be measured. As the liquid level changes in the tank, that liquid level is also duplicated in the chamber. So liquid level rises and falls in the tank. It also rises and falls in the chamber that we've connected to it. And inside of that chamber is a float, and we'll talk more about the floats in a little bit. The float contains a magnet system, as we've talked about a little bit already, and then mounted outside of that chamber, though, totally separate from the process, is what I call a bar graph indicator. It's a an indication system that reacts with movement of the float. So basically the liquid level rises and falls in the tank. It also rises and falls in the chamber. The float rises and falls upon that liquid level, and then it causes a reaction magnetically with an indicator separate from the process on the outside of that chamber. So here's another kind of a view of it, and basically I'm going to review that we have basically three parts to it. There's the chamber, the float, and the indicator. So we're showing on the right drawing kind of an X-ray vision, an X-ray picture of it, and inside there is the float. And there's always a lot of questions and comments about the float. Why can't you just make it a round ball? Why does it why does it have to be? Why can't you make it skinnier? Why can't you make it this shape and that shape? And we'll try and touch on a little bit of that, but basically this is kind of a vision, a view of what's going on. We've got the two process connections on the side. Not saying that there should only be two, but that's basically what you'll need to duplicate the level inside of a tank. And then you'll have the float rising up and down, and then the indicator mounted outside of that. So what is the chamber? Let's talk about that a little bit. The chamber, basically, it's a piece of pipe and its flanges. And because of that, this instrument often goes in the department of a mechanical item or a piping item, and as it probably should be. It's a piping component, and so obviously we will build it to meet the application, but sometimes our customers or any customers will have a list of specifications of how to build them. And of course, a manufacturer of these types of instruments should be able to comply to any of those specifications to make sure they meet the piping specs for a plant or a facility in which they are installed. But first of all, this pipe and these flanges, well, not necessarily the flanges, but the pipe, the chamber we're making this out of should be a material that is not attracted to magnetism. You know, when you stick a magnet on your refrigerator, it does not slide up and down on that refrigerator. It stays right there. And so if we made this pipe out of carbon steel and then we put a float with a magnet in it, that magnet would stick right to that pipe at the spot you put it, because carbon steel is attracted to magnetism, and so the float would stick to that pipe. So the most common material to make this out of is a 316, or excuse me, a stainless steel material. 304 or 316 are the most common. There are needs sometimes to make these out of some exotic alloys and so on. The reason for that is, well, as great as stainless steel is, there's some nasty stuff out there that corrodes stainless steel, and so we need to make the chamber out of other materials as well. So we can do that, and here's some various ideas of some of the materials we'll make it out of, but we have a long list of other ones too. We'll show you, but the point is, in choosing this, make sure that it's not attracted to magnetism. Now where we kind of get stuck sometimes is Monel or duplex. Monel can be very attracted to magnetism, and we have to be very careful with it. Sometimes we found that it depends on the run of the Monel when they're making it. But another thing about Monel is, at a higher temperature, it reaches what's called the Curie point, at which it is not attracted to magnetism further. And high temperature Monel applications are very good to do, or are fine to do, I should say. The Monel is just tricky to work with. Of course, it's very expensive, so you got to be careful working with it. We do have some customers that ask about duplex stainless steel, and these are more for offshore applications, so I don't know if we need to discuss it right now, but duplex stainless steel is a material that is very attracted to magnetism, and so it's something we do get requests for often, and we have to ask for other types of materials as a substitute for that. So it's one of those things we have to be very careful about when we're building these. It's funny because we still do have a lot of customers that ask for these to be made out of carbon steel, and I think there's two reasons. One is the process vessels might be carbon steel, and so an engineer might forget about the fact that this is attracted, carbon steel is attracted to magnetism, and say, well, that metal is good for my process, and so it will be for this gauge too. It's a piping component. Another thing that I've discovered is that old specification sheets for glass gauges, like the reflex gauge I showed you in an earlier slide. Yeah, well, 90% of those or so are carbon steel, and so for years these types of instruments, a visual level indicator, had been made out of carbon steel. Well, as we shift into magnetics, well, we can't do that. So we are able to make the chambers out of other materials too. We can do them out of PVC, Kynar, Teflon, and so on. We don't get a lot of call for those, and it's not a big part of the magnetic level indicator market. But there's some folks who do like the PVC. It's a lighter weight. It can handle a lot of the chemicals and that might be difficult to do with stainless. And it's going to be a lot less expensive than like a Hastelloy or a Monel. So these are options for us to manufacture magnetic level indicators out of, and you know, they work very well. Pipe comes in various sizes and thicknesses, and we're going to talk about that in our next slide, but it's all going to be application dependent, and I'm going to stress that because a lot of folks say, hey, they might call up and say, hey, I'd like a 2-footer, 150-pound flanges, you know, what do you got? And if it was that simple, this would be a great, easy catalog item instrument to sell. But it is engineered specifically for every single application we look at. So it makes it a little bit challenging sometimes. And we'll talk about that even more when we get into the floats. A little bit about the way we can do the construction of the chambers is we can, obviously we're dealing, like I said, with pipe. And so different wall thickness pipes will withstand different pressures. I think this is pretty elementary stuff, but we'll obviously want to make it out of as thin wall as possible because we're dealing with magnetic strength. Magnetic strength decreases exponentially with every millimeter you get away from the magnet source. So we want to make sure we capitalize on every bit of every amount of magnetic strength we can have. So if we can build it out of the thinner wall pipe, we'll build it out of the thinner wall pipe. Now this is fine for many basic and simple applications and so on. What we have found that there's many of our customers want have plant specifications in which they want this instrument, which is now, like I said, it's kind of a piping component, to match their piping specifications for the plant. And so, yeah, although it makes it a little bit more challenging for the manufacturer of these instruments to provide that, it's definitely doable. It's just something that has to be put into thought and design as we are putting these things together for you. So we can make some pretty basic magnetic level indicators, and then they can be some pretty stout ones as well. Pipe size will vary as well. I mentioned here that we can do 2-inch, 2.5, 3-inch. We've done some bigger chambers as well. Once again, we're going to be dealing with a float with a magnet system in it, so we want to optimize our ability to use that magnetic strength. So you got to be careful in varying the size of the pipe, but we take all of that into consideration, and it's all a function of your application. Temperature, pressure, and specific gravity. And I can't stress this enough. I even say this to any sales guy who's learning how to sell this instrument. You can have 2 out of 3 of these specifications here: temperature, pressure, specific gravity. But unless I have all three of them, I really can't even design this thing. It really is a function of understanding how the pressure reacts when we're designing it, and then adding a difficult specific gravity or even a high temperature can really affect what pipe we use, the diameter of the pipe, and so on. And all that plays into the float, which we're going to be talking about next. Oh, well, in a couple of slides, excuse me. Now, how we build the chamber is very important because the chamber has to have the branch connections on it. Those are the connections off of the side of the chamber that will obviously give your process, connect to your process. And it seems simple enough, but if you've made a branch connection that causes an interference with the float travel, well, then we might have a problem. And let me explain what that means. For example, let's just look at option number 2, a welded T. And there's a chemical plant in Canada that likes all of their chambers to be built with welded Ts. And for the most part, that seems like a really not good way to do it, because you're simply welding a flange directly onto that, and then you can bolt it up as your process connection. Very simple, very easy. But this can cause a lot of headaches too. First of all, if you look at that, remember, we have to have a float riding up and down inside of this chamber. And you have 2 weld points to connect that T onto your chamber. When you weld onto that chamber, there's a good possibility that you can cause an area of hindrance, interference with the movement of the float up and down. So you have to be very careful how you do that weld. Now, if you're got some good skillful welds, as most magnetic level indicator manufacturers do, it shouldn't be a big issue. However, sometimes there's not that big a tolerance. There's not that big a difference in the diameter of the float in the pipe. It's pretty tight in there, and so you got to be very careful with that. Another part about the T's is when we've noticed when you go to a pipe supplier, a piping fitting supplier, when they manufacture these T's, they don't necessarily use the same inner diameter or the same standards that your average pipe manufacturer will. So let's say we're making a chamber out of 2-inch Schedule 40 pipe, and we go buy our pipe, and then we go buy some welded, we buy some T's to weld onto it. We're going to find that if we measure the inner diameter of that T, it is probably going to be a lot less than the inner diameter of that Schedule 40 pipe. I don't know why that's the case, but we have a sister company in London, England, that actually has a customer that requires the use of welded T's. So they actually have a machine shop that bores out the T's for them so that it does match the inner diameter of the Schedule 40 pipe. And in doing so, still keeps the T within the standards for being Schedule 40, but then also make sure it matches the chamber. So it is extra work and extra time and effort. It can be done, but you got to be very careful. My point on this whole speech is that in building the chamber, we have to remember the float needs to travel up and down past those process connection areas, and so care has to be taken to doing that. If you look at option 1, that's called a saddle weld, because we could be cutting a saddle shape on the side of the pipe. It's easy and it's doable. You have to be careful when you heat up the pipe right there. And if you put too much heat when you're doing your weld, it can cause warping of the pipe. And same when we do use the OLEDs. It's standard practice to do all of these things for making chambers, but care has to be taken. You have to be very careful when you do the OLEDs. The reason we would add an OLED is by code. Sometimes when you have a higher pressure, the pipe pass the code calculation, but where the branch connection is, it might be a little weak, and so we have to beef that up a little bit. And one way to do that is to add an OLED there in that area, and that way it passes our code calculation. A fourth way to do the branch connections is with a process called extrusion, and as you can see in the picture there, this is like a shape we form on the side of the pipe, and then we can weld our process flange directly onto that. But in doing so, this does not distort the pipe with any welding. It does not add extra welds into the area. It makes for a less expensive magnetic level indicator, and that's good for everybody involved. It's not for everybody. We found that it's very popular with many customers, and it works very well with as far as good, smooth float travel and so on. But when it comes down to some of our customers want a larger, let's say a larger scheduled pipe or a larger diameter pipe in which extruding is not possible to do, and then we can revert back to some of the older ways to do the, some of the other ways to do the branch connection. So the way it works, just real briefly, then we'll get off of this subject, is we bore a hole in the side of the pipe, and then if you notice that hole in the top left drawing is kind of in an oval shape. The next step in is that a tool goes into that hole, and then it pulls and forces the shape on the side of the pipe, and then we mill off the top of that, and that gives us a good smooth flat area to weld a process flange on or a branch connection on. It doesn't get in the way of the float travel, and you have a very good magnetic level indicator without the possibility of a float and possibly getting stuck at the branch connection. So any way you do it is fine. The key is we need the float to be able to move up and down. There's a major chemical company in the world, and they use magnetic level indicators, and the guy who's on the level team for that chemical company says, I just don't want to use old mechanical float devices in my plant, but I have to use magnetic level indicators because I don't want to use glass gauges. And so the key is to make sure these things are going to be without fail, continue to work, low maintenance, and made the best way possible. And so we, as manufacturers of these, have to make sure we have good, smooth float travel in that chamber, no matter how we build them. So let's step into the float portion of this now. The float is really kind of the heart of the matter. It's very important to build a float, and they are built specifically for each application. As I mentioned before, the float does contain the magnet assembly. They're kind of tricky to build. We need to put a magnet in that gives us magnetic force all the way around the float, 360 degrees around the float. The float could be in there bobbing around, spinning around, yet it still has to cause a reaction on the indicator mounted outside of the chamber. And so it's tricky to put a magnet system in like that, but it's doable, and there are a few different ways of doing it. Floats are most of the time, I say stainless steel, but most of the time they're titanium. Why are they titanium? Well, the main reason for titanium is its lighter weight. And so when we're dealing with a float, we need to make an object that's going to be buoyant, that floats upon the liquid. And you're dealing with a metal, though, and that can get a little bit heavy. So it's got to be built and designed so that it can be buoyant upon the liquid, whether it's a high specific gravity or a very low specific gravity, and that makes it very challenging. Adding pressure and temperature into the mix really makes it challenging. We can make floats out of Hastelloy. Hastelloy is a heavier metal, but as we mentioned before, we make chambers out of Hastelloy and Monel for really difficult applications, and so the float needs to be able to withstand the same corrosion compatibilities as the chamber. So stainless is great, titanium is lighter weight, can be stronger, and then Hastelloy, Monel. Sometimes we have customers that want the floats coated, and the reason for this is it might be something that's very difficult to build a float, and as far as making sure it has the right buoyancy and understand, withstands the right pressure. But we can put a Teflon coating on the float, and that's kind of like, coating your frying pan. That way we make sure nothing's getting through to that surface. I shouldn't have said frying pan, because Halar is really why we put a coating we put on for lubricity. It's to make sure that we don't have stuff adhering to the float. So that's more like a frying pan. But Teflon is for making sure we don't have the float corroding in a nasty process too. Okay, and then floats can also be plastic. Remember, we were making the chambers out of PVC, Kynar, Teflon. We can also make the floats out of those materials as well. In fact, we had an application in-house just a couple days ago where the customer required alloy 20 chamber, and we would then, I don't think we'd make floats normally out of alloy 20, so we were looking at Hastelloy or another material, and we checked on Kynar for a float, and it turned out that that would be pretty compatible with their process, so we were running it by that customer. So here we would have a Kynar float inside an alloy 20 chamber, and actually that's a cheaper option as well, and it's a very buoyant material to make a float out of, so it might work well. Floats. I'm going to show you a few pictures of some of the floats we've manufactured and over the years. If you look at the left side of this, the floats, basic titanium floats. We have a customer in northern Oklahoma that calls it the pill. They said, yeah, we dropped the pill out to make sure everything was fine, and so on. And at any rate, the float is, if you look at the second one from the left, that's probably a float for a higher specific gravity like water. Basic, not too high a pressure, not too high a temperature, and a pretty easy specific gravity. What gets challenging is when you have the really lower specific gravity and then higher pressure application. So take, for example, the float that's second from the right. That's a titanium float that might be used for propane. Now, propane, as opposed to water, has specific gravity around let's say 0.5, maybe sometimes 0.45, but it's a lot less than water. So that float has to be a lot more buoyant than a float would be for water. Now take another part of that equation, and we know that propane for the most part is a gas, but we make it a liquid by adding pressure to it. So propane could be under pressure of 1400 psi. So different than water, which might have, atmospheric or maybe 100 psi. Here we got propane not only has a lower specific gravity, but a higher pressure. And that makes it really challenging to build that float. We have to make sure that there's enough area to give it enough buoyancy to float upon the lower specific gravity. But then we've got to make it strong too. We put 1400 psi on their average float, and then it's going to crush. It's just going to look like you drank all the water out of your water bottle and you crushed it with your fist. And I've seen floats that look like that. So what we have to do with the higher pressure floats is the tubing that we manufacture the float out of has to be a thicker material. And then we actually have to put strengthening rings, retaining rings. It's kind of like a skeleton on the inside to make sure that it adds strength to that float so that it won't crush in the higher pressure. Well, as we do those things, as we use thicker tubing and as we add the strengthening rings, what happens to the float? It gets heavier. So now we're fighting another battle here. We're adding more weight to this thing, yet we need it to be able to float on a low specific gravity liquid, and it's a real challenge. And it's something that's very difficult to do, and then that is why every single one of these floats need to be engineered for specifically for our customers' applications. Temperature, pressure, specific gravity. The one on the right is a Hastelloy float. Once again, I mentioned Hastelloy is a heavier metal, and so therefore it has it is another one of these more challenging ones to be buoyant upon some of the lower specific gravity liquids. And unfortunately, some of the real corrosive ones are. So one other thing I want to touch on is the diameter of the float. I once went to a chemical plant, and the customer said to me, you know, I don't understand why you guys can't make little skinny floats so that there's more room around it. And he goes, to me, you're not giving yourself that much room around the float. That thing's just going to get stuck. Well, agreed. Absolutely agreed. And that's why I talked about the way we build a chamber. We have to build a chamber making absolutely sure that the float does not get stuck. But we can't make a little skinny float in there. And the reason for that, I've already mentioned, we're dealing with a magnet. And although we can put the strongest magnets we can find in there, if their float is let's say we have a 2-inch chamber with a 1-inch diameter float. There's a lot of room, and I literally wiggle room inside of that chamber for that float. And like I said, that magnet gets weaker exponentially with every millimeter away from it. That's going to be a really touch-and-go instrument there for you. It might be far away from the indicator at one point and then close to the indicator at one point, and you just don't know if you're going to get the accurate reaction that you need. And so our challenge is in designing these is to make that float fit as best in the chamber as we can, giving it enough clearance for good enough travel, and yet making sure that we also have magnetic strength good enough to cause a reaction to the indicator. A couple more floats that I want to show you. This is one that our German counterparts came up with. Actually, both of these are. They call it a foam float, and I think that's just because there's not really a good translation for whatever word they were using to describe it. It's kind of a plasticky material. It's like a solid chunk of this plastic. It's I don't know, it's not like a polypropylene or ethylene type of material. It's a strange material, but at any rate, you could drive a truck over this thing. We've put some very high pressure applications. You can't go too high with the temperature, and it's made for specific gravities like 0.8 and up. Maybe we can go lower than that, but and it's for mostly non-corrosive fluids. So we've put this in, and there was a fire water system at a steel mill that could withstand, that needed to withstand 3,000 psi, and they had been through a magnetic level indicator before, and it was crushing floats, as we talked about earlier. And then they put glass gauge in, and that just was not what they needed, and they called us up, and we put one of these in, and they've been very happy with it ever since. Another application is there was a compressor, high pressure compressor, where the lube oil was in a tank up to 5,000 psi, and we are tracking their level very, very well with this type of float. So that just kind of gives you the flexibility of these types of instruments and what they're able to withstand and do. The next one to the right is what's called a titanium spherical chain float, or a ball chain float. And the best way I can describe this is, you know, you take a sphere, and a sphere can withstand quite a bit of pressure, much more than a cylindrical object, as we all know from high school physics. But a single sphere with a magnet system in it might not be buoyant enough. It might not have enough area to be buoyant on the liquid that we're measuring. So what's the best way to do that? Well, to increase the area of it. Well, we can't increase the size of the sphere unless we made it bigger and wider. And so pretty soon, you know, you might have a low specific gravity, high pressure application and a sphere as big as a basketball. And that makes it pretty much impossible to make a magnetic system and a chamber big enough to withstand that. So what we then do is take multiple spheres and we put them together. So here we have we're increasing the buoyancy of this float by adding more and more spheres to it, and they're tack welded together by thin strips of titanium material so that it retains its light weight, and then also is able to handle very high pressures. And we can do high temperatures with it, a very wide range of specific gravities. I had one of these on my desk last week that it was actually 10 spheres welded together for a lower specific gravity, high pressure temperature application. So it's just kind of an interesting thing that there are options with this technology that give us a lot of flexibility for many different applications. Let's see what else we have. A little bit. Magnet systems vary depending on the manufacturer of magnetic level indicators, but this is a similar system to what I described as the patent in the beginning of the presentation, where they make a system in which only the North Pole, the flux of the North Pole magnet is surrounding the float. Some other manufacturers out there have both the North and the South Pole making a flux ring around the float. Either way is fine. What I found is with the North Pole out system that it might just cause a reaction of 1 or 2 flags at a time versus multiple flags. But either way, it is the key. The thing to take home from this, it is very tricky to make a magnet system that really is going to give you that 360-degree flux pattern around the float to continue to cause an effect on the indicator outside of the chamber. Okay, so indicator now we're going to talk about, and I guess I should have just said how an indicator works, but this is kind of let me tell you a story. I love telling this story. This one time I went out to a chemical plant and I said, hey, look, I'm here to talk about a magnetic level indicator. And I put my little demo piece on the desk, and I was all excited because I think this is the greatest thing since sliced bread. And the customer says, no, don't want them, don't like them, don't want to use them. In fact, get that out of here. And I said, whoa, hey, this is great stuff here. What's the matter? And he said, you know, I've used those before, and I don't like them. And the flags stick. I'm like, what? So we went out in the back of his plant, and he showed me a little application, and there was a magnetic level indicator. And sure enough, the flags were all rotated in all different directions. It was 5 this way, 6 this way, 10 that way, 4 this way, up and down. And he goes, you know, can you see where my level is in there? I said, yeah, I got to say I can't. He goes, I don't want to use these. Well, what happened? What was going wrong? What was going on in that? Well, that just kind of lets us know that it is not easy to make these indicators, and it's tricky. Now, what's going on with that particular indicator is you got a flag, whether it's red, white, yellow, black, orange, whatever, but it's on, I call it an axle. It's on a pivot point, and it rotates on that pivot point as the float rides up and down in the chamber. A lot of times that pivot material is some kind of steel, and that's fine, but then that pivot, that little pivot or that axle is mounted in an aluminum track, and so these two dissimilar metals might work fine and rotate very nicely, but let's say moisture gets in there, and sometimes these things do get moisture in them. Somebody might, even though they're hermetically sealed, they could get banged up or cracked, and so on. And this particular one wasn't sealed well enough. Moisture got in, and it caused some corrosion to take place on those pivot points, and so the flags were not rotating. And that not only made that manufacturer of the magnetic level indicator look really bad, it made the technology of the magnetic level indicator look really bad, and it made the customer very upset. I don't blame them a bit. One of the key things you should take into consideration in putting these indicators together is making sure those flags do rotate very nicely without getting stuck. And one of the best ways to do that is to have similar metals rotating on each other. So what we've done, and I don't know if some of the other folks have done it too, if you look in the bottom left-hand corner here, that's a stainless steel carriage piece with all completely stainless steel flags in that carriage piece. So everything is stainless steel. Stainless steel pivot points rotate very nicely. You'll also see that there's a magnet embedded in that upper piece, and you're going to find this on many of the magnetic level indicators out there. There's going to be a little magnet there. That magnet is what causes the rotation of the flag. The float rises, it pulls that magnet, or it attracts that magnet to rotate, and goes into position. The other beauty of that is that each flag has that magnet, and so as they rotate, they kind of lock to each other in the position that they're in and stay in that position, and until the float passes back down and attracts them the other way. So it's a nice, it's a neat system. A lot of people don't understand how much really thought kind of has to go into those flags to make them work, but there's lots of ways to do it. But the key is you got to make sure they work, or they're just not going to be a useful instrument. And so now we've talked about, we got to make sure the chamber's built right. We got to make sure the float is able to handle the application. You got to make sure that the indicator is working in conjunction with all of it. Otherwise, it just isn't a complete instrument. And I've seen so many customers come and say, hey, I want to replace this part and that part and this part. And to me, it's like taking a pressure gauge and switching the board-on tube out with another one and making it work that way. You really have to have the whole thing designed, engineered, put together for it to really work very well as a system. Now, there's other parts that come with this type of a product, and more folks are wanting us to build chambers, and I'll describe why in a little bit. Folks want us to put valves on these things because they want a drain or a vent valve, or they might want process valves, and that's easy for us to do. As you can see in the picture here, there's some threaded on there, but often it becomes part of welding to weld valves onto these, and any manufacturer should be able to weld on valves that meet your specifications as well. More and more folks want transmitters associated with these switches. I'm not going to spend a lot of time talking about this because I really want to just focus on the magnetic level indicator part of it. And then insulation, it becomes very important, and then sometimes heat tracing and steam tracing and reinforcing it with gussets. So I'm going to show you just a few pictures of these. First of all, it's been very popular to start manufacturing magnetic level indicators in conjunction with a guided wave radar. And I think it's a very good design. We can either do a dual chamber design as we're showing you in the center, and just about any manufacturer can do this. And in that way, you can throw a guided wave radar on in the same process connection that you do have your magnetic level indicator, and you have now an output from that chamber. Now, some folks want separate chambers completely. So if you look on the far left, we have a chamber there that's a magnetic level indicator, and then we have valves separating it from a guided wave radar chamber, or whatever type of chamber. Or if you look in the right picture, you see the process connections in the center with T's, and on the right-hand side is the magnetic level indicator, and on the left-hand side is a chamber for a transmitter. All of these things can be done. We have the capability of doing a lot of that type of stuff. I want to touch quickly on a transmitter that's been around. The reason that I showed you that slide at the beginning that showed you the KSR Kubler company, it's a company that WIKA bought around 2008, and they had been in business for making instruments with reed chains, with reed switches. And they make high and low level switches and float switches using reed switch technology. Well, they can also put them into a transmitter, and what they do is they put a bunch of these reed switches on a circuit board and a transmitter, and they basically make a resistance loop through there, and as each reed chain makes, it increases the resistance. We basically then can translate that resistance to an analog output. This is not something new. This has been around, like I said, since the 60s, and the thing about it is it's rugged, it's reliable, and it works very well. Now you can have a magnetic level indicator. You don't necessarily need a separate chamber for guided wave radar. You can slap one of these transmitters on the side, and you've got a nice analog output for your level signal. That really is a difference if you look at, remember that beginning picture I showed you, which showed the reflex gauge on the side of that tank. Now you take what used to be just a visual indicator, you throw a transmitter on it, and you've got an analog output. Another one is a magnetostrictive transmitter, and I could probably do a whole hour talk on how magnetostrictive transmitters work. But just really quickly, I'll show you this picture if you can follow me on this. The silver tube down on the diagonal here, that's like a sensor tube. Now what we do is we send a current pulse down that sensor tube on there's a wire in the center of that thing. It's held very tight, a magnetostrictive wire in the center of that tube. So we're sending a current pulse down there. Now when the current pulse comes in the area of a magnetic force, and that's what these red and green things are, is supposed to be a magnet that's embedded in a float. That current pulse, when it hits that, when it hits that magnetic flux area, it actually causes a torsioning movement of that magnetostrictive wire, and that is picked up on the crystal sensor up at the top, and there's different ways to do that sensor and so on. So basically, review, we're sending a current pulse down, it's hitting the magnetic area, the magnetic flux area, it's causing a torsional wave that we measure on that crystal at the top. We're measuring the time of flight at which it takes to send the current pulse down and receive the torsional wave back up at the sensor. And in doing so, we can very, very accurately measure distance, and then we can convert that into, well, level measurement. So you can put a float on this silver sensor rod and have a nice float transmitter, or you can throw that transmitter on the side of a magnetic level indicator. Why? Well, we've got a magnet in that chamber that's causing a reaction on this indicator. It can also cause a reaction on that magnetostrictive transmitter. So that's a very, very popular means, once again, as well as the read chain transmitter, of giving you an analog output from a visual indicator attached on the side of your tank. Another thing folks want is they say, hey, I got great visual indication, can you give me a high or a low level switch? And once again, we can do that. We can make a switch that you throw on the side of this magnetic level indicator that gets that as the float passes by causes the switch to make or break. And now you've got your high level switch or your low level switch, or we've actually provided some of these with 4 or 5 different switch points on them. You can put as many switches on here as you want. As long as there's room on the chamber, we can strap the switches on there. The beauty of all of these instruments, the transmitters, the switches, and so on, is they are external to the process. You can, if you needed to, you could work on them, you could replace them without shutting down, and you still would have visual indication of what's going on in your process. You could buy a magnetic level indicator today and then call up a year later, say, hey, you know what, I love this thing, I want a high level switch, or I love this thing, I want a transmitter. Easy to do, simple to do. And any manufacturer can go ahead and provide one of those for you. It really makes this instrument so versatile. Once again, from the evolution from the glass reflex gauge to this is really added so much to what a plant is able to do with just a visual indicator. Okay. Sometimes, well, you make these magnetic level indicators and you put it on a hot tank, and well, doggone, you want to keep that process hot, or more so, more importantly, you want to keep your people safe. A big boiler or a hot type of application, the tank might be completely insulated, and so might be all the associated piping. We have to make sure this is insulated as well. So we provide insulation on our instrument. That way we make sure that it's built correctly for the instrument to make sure it still functions correctly even in those high temp applications. We can do other things like where there's a temperature that's really cold. The picture on the right is something we did. There was a plant in Ohio that had a liquid level that they were worried about freezing in the winter time. So we put a freeze protective type of insulation on it. Worked very well. Now this is something that's kind of funny. I get humor out of this, but you folks might know exactly what it is. But this picture was taken in Oklahoma in the middle of summer. It was a very hot day. But this was a reflex gauge that had been out there, and somebody had taken the insulation off of it because they basically couldn't see the gauge with the insulation on it. And so what happens? Well, you've got moisture in the air, you've got a humid day, moisture condenses, it freezes immediately, and then it continues until you got these big ice balls on the side of this tank. So what do you do about that? Well, you can chip away at the ice till you find where your level is, but that's really not going to do you any good. In fact, in this case, it's probably full all the way up since it's completely frozen. Who knows? We can do a magnetic level indicator to handle that type of an application very well. So we start with the chamber, and we put a different kind of an indicator on with a little bit of an extension on it, and then it can be covered with a foam glass insulation, which we seal up, and then we completely enclose it in an aluminum cover, and now you've got a cryogenic type of magnetic level indicator that you can easily see where the level is, and yet still will withstand, or excuse me, won't have the ice build up and be virtually a useless indicator as that other one was in the prior picture. So you've got that going for us. So steam tracing. Sometimes, like I said, you've got a hot liquid and you want to keep it hot. We did an application 2 weeks ago. The customer said, yeah, we got wax. We want to make sure this wax stays liquid. In our tank it'll stay liquid, but we're concerned because we're putting a piece of piping on the side of the tank that might be a lot cooler than what it is inside the tank, so they wanted steam tracing for it. And there's different ways to do this steam tracing. A lot of folks just strap a piece of tubing up and down this chamber and then have it extending out so you can put your tubing fitting on. Another way we've learned to do it is to go ahead and make a little termination block so that we can run the steam up and down, have it tacked to the chambers, whether it's these are level chambers on the right. You might notice those are carbon steel, and that's a magnetic level indicator on the left with steam tracing on it. Also notice the flanges, the valve is welded on, and that's common to do. We have some customers that have really high vibration applications, and they want to make sure that even if they have a lot of vibration, we're not going to tear apart our weld. So they've asked us to weld extra gussets on that make sure that they withstand that vibration. Another reason they might want gussets is we've had some customers that want a foot or maybe 2 feet of piping between their chamber and their process connection. And that can really be a strain for a magnetic level indicator. So we will build those with gussets so that it makes sure it withstands the weight. Just something else that is possible to do with magnetic level indicators. So I'm going to go over some of the specifications and things that you need to understand and know that anybody, well, not anybody, but a magnetic level indicator can withstand. So temperature ranges can range from -320 to 1,000. Why only 1,000? Because that is the point at which magnets lose their strength. I talked about Curie temperature before. There is one type of magnet that can withstand 1,000 degrees Fahrenheit, and that's the point at which it loses its strength. Pressures, full vacuum to 5,000 psi. Some folks don't have the capability to manufacture those types of floats up to those pressures or even actually those temperatures, but it is doable, and that's probably the max you're going to get out of this instrument no matter who makes it. Specific gravity, 0.35 is kind of that's when it gets challenging. Some folks can do a little bit lower than that. Now you start adding a higher pressure and a higher temperature to that low specific gravity, and that's not a good mix. It just ain't going to work. So there's ways to run calculations to figure out all of these things, of course, but that is kind of a limit there. These can be all different lengths and sizes. 20 feet we say is a standard, but it's a matter of how you can ship it when it comes down to it. You can't ship anything over 30 feet really easily. So I've seen some of these things 45 feet. We've quoted some longer, but it's difficult to ship. That's what our holdup is on that. And the wide range of materials, like I said, we talked about some of the exotics before. I love it when people come to us with 347. Boy, I'll tell you what. It's good if you can. We run calculations to make sure that we're building everything to meet ASME B31.1, B31.3. It's good to have a good engineer in-house. A PE on staff makes it very good. Don't get a lot of call for needing PP stamp on it. Sometimes we do, and sometimes folks want a U stamp on it. There's a few manufacturers, magnetic level indicators, that can provide a U stamp on the chambers. We rarely get a call for that. Sometimes they want NACE certification on the chambers we build, or ABS for shipping. Or if they're shipping to Canada, because this is a pressure containing device, it has to have CRN, so a Canadian registration number in each province. There's a different one. it's good to have a lot of welding procedures on hand, and sometimes customers, some of the refiners have their own procedures, and that's fine. We've got many of them, and I'm sure other folks do too, but it's good to have the flexibility to apply different welding procedures to meet different customers' needs and requirements and so on, and have good code certified welders as well. Just real quick, here's one of our applications where there was an old reflex gauge out there for years, and we were able to take it out. Honestly, we could have taken this whole bridle out and got rid of that float switch on the side, but they didn't want to do it. But we put a magnetic level indicator with a dual chamber and a guided wave radar on it, and they love that thing. It's been working very well for them. So that's kind of a quick run through of what a magnetic level indicator is, what it's able to do, and how we're able to handle so many visual level indication applications for you. So if you have any questions, I think I got a few minutes left in which I can fit some in if anybody has any.
And when you showed the materials it can be made out of, I didn't see this in the list, and that's aluminum.
Well, that's a great question. That's a good question. Actually, we've never had anybody ask us to make it out of aluminum, but you're absolutely right. It can be done. And we make some of our demo pieces out of aluminum. I don't know how well that they withstand, the aluminum withstands pressure. I don't think it would handle vibration, and especially the branch connections might not handle the weight too well. But actually, when you're dealing with aluminum, it might not be that too much weight, but it's doable.
Okay, so it can be done.
Can.
I'll start to wrap up here. As I'm wrapping up, if somebody does have a question, please just type it in and we'll make sure we get it answered. Jim, I'm going to take over the screen from you real quick here if I can.
Okay.
All right. Again, Jim, thank you very much for your presentation. If you do want to know more about the technologies we supply, please follow us on social media. Dan Wisey's blog is very active and has tons of great tips. You can see that there under blog.lesman.com. All of our webinars are posted to both our website and on our Lesman Instrument Co. YouTube channel. And you can see it there at the bottom as to how to get to the YouTube channel. If you want to know when something new is posted, please follow us on LinkedIn or Twitter because we do post them there as well. In December, we will be hosting a webinar to talk about a very difficult application, measuring the flow of dry solids. If any of you have ever tried measuring the flow of dry solid material with changing density or moisture, it can be very difficult. You can tune in to hear Becky Allegius from Ronan Engineering talk about how they've mastered the application with radiometrics. If there are some other topics that you would like us to cover in our webinars, please send me an email at just miked@lesman.com with the subject, and we'll find a subject matter expert to see if we can't put that together. We have lots of access to product and process specialists, so again, please send me your ideas. At this point, Jim, I don't have any further questions.
All right.
So I want to thank everybody for attending, and Jim, thanks for putting on a great presentation.
Mike, thanks again for the opportunity.
You're very welcome. Enjoy the rest of your day.
You too. Bye-bye.